Hey everyone, Umang this side. It's 9 p.m. and I am very hungry. So I open the Zomato app and then within milliseconds I see dozens of restaurants near me. Seems simple, right? But here's the thing. Zomato has millions of restaurants in their database. So how does it find the nearest ones so quickly? So today we are going to reverse engineer this system. We will explore four different approaches from the naive solution that absolutely won't scale to the production grade solution that power apps like Zomato, Uber and Google Maps. By the end of this video, you will be able to understand the exact trade-offs and why companies choose what they choose. So let's dive in. Before we jump into solutions, let's define what we are solving. So when you open Zomato at, let's say, in Kormangla in Bangalore, what is the input that you provide? That is your current location, which includes your latitude and longitude. And what is the output that you expect? You expect all the restaurants within, let's say, 5 kilometers sorted by distance. And what is the scale that we are looking at? Say for suppose you have 500,000 restaurants stored in Zomato's ecosystem and millions of users are querying simultaneously. And the response time we are targeting is, let's say, 200 milliseconds. And here's the critical constraint that we need to do this fast. We can't scan through 500,000 restaurants for every single query. And that is going to be the core challenge. Okay, so let's start with the most obvious approach and see why it fails. The simplest solution is to store every restaurant with its latitude and longitude in a database table. And whenever a user queries from a location, let's say Kormangla, which is, let's say for suppose here, we calculate distance to every restaurant, every 500,000 restaurant, and we bring all those restaurants within a circle of 5 kilometer sorted by distance. And this is how the query will look like. For reference, I have used the Euclidean distance formula over here, but in real life, we use something known as Heversine formula, which involves trigonometric functions as well. So we calculate the distance, and then for all the restaurants with distance within our radius, we sort all those distances and we bring only, let's say, top 20 restaurants. Okay. Why is this solution terrible? It is because we are checking all 500,000 restaurants for every query. Okay. And we will use Heversine formula that involves trigonometric functions, which is expensive. And then we are not using indexing because standard B-tree indexes work on one dimension. And here we have two, which is latitude and longitude. So we can't efficiently index 2D data with traditional databases. Okay. And if you do some math, you will understand that if each distance calculation takes 1 microsecond, scanning 500,000 records takes 500 milliseconds. And you add sorting on top of it. So if you're looking at 1 plus second per query with 10,000 concurrent users, your system is going to crash. And this is where engineers go wrong in interviews. So they stop here, but we are just getting started. Okay, so let's think differently. What if we divide the entire world into grids? Imagine overlaying Bangalore with a grid of 1 kilometer square. So now instead of storing just latitude and longitude, we also store which grid cells each restaurant belongs to. So this is how our database table will evolve with an additional grid ID for every restaurant. Okay, now how the querying will work. Say for suppose your user location is present over here. Okay, now we only query restaurants in this cell and the 8 surrounding cells. That is, we will query only for these 9 cells because these are the closest restaurants. And in this area, maybe let's say there are 1,000 or 2,000 restaurants. So instead of scanning 500,000 restaurants, we scan maybe 1,000 or 2,000. And that is nearly 200x, more than 200x faster. But what is the problem? The problem is uneven distribution. All these cells will not have equal number of restaurants. Lot of cells might not even have one single restaurant, and some cells might have 100 or 200 restaurants. Okay, so there are two critical cases. Think about a 1 kilometer square area near Phoenix Market City in Bangalore, which is very dense, super dense, which might have, let's say, 500 restaurants, but in the same grid, in a residential area, which might have just 2 restaurants, and in rural areas, maybe 0. Okay, so the issues are hotspot cells, which means that dense areas still require scanning thousands of restaurants. Okay, and there are so many wasted cells, which means most cells are nearly empty, wasting storage. Okay, and there can be edge cases like if you are at a border of a cell, the radius is, let's say, 5 kilometer, not just 9 cells you need to scan, but you might require to scan, let's say 50 or 20 cells, and which is not efficient again. But a cell, say for suppose in Whitefield outskirts, might just have 5 restaurants. So we need something smarter. We need something more intelligent, something that adapts to density, which is not solved by the uneven distribution of dividing the planet into grids. And this is where enters Geohash. Okay, so the grids don't work well because of uneven distribution. And let me introduce you to Geohash. Think of it like a smart postal code for every single location on Earth. Okay, so the core idea is, what if instead of storing latitude and longitude separately, we could convert them into a single string, like a zip code, okay, that represents a location. And here is the genius part, that nearby locations would always have similar strings. Okay, so now let me explain geohash in simple terms. And for that, imagine you are playing a game of 20 questions, okay, to find your location on Earth. So instead of asking some random questions, you ask very specific ones. So the step one is your location in the eastern or the western hemisphere? If the answer is in the eastern hemisphere, you just note it as 1. So say for suppose your location is in the eastern hemisphere. This is the eastern hemisphere. Okay, this is your whole Earth, where your location that you are present at is in the eastern hemisphere. So you just write a 1. Now within the eastern hemisphere, you ask another question. Within this eastern hemisphere, is my location in the north or the south? So is my location in the northern or the southern half of this eastern hemisphere? Let's say your answer is north. So you write again a 1. So for east and if your answer is either east or north, you write a 1. If your answer is either south or west, you write it as 0. So first answer was east. Now the second answer is within this, my location is in the north. So you again write a 1. Does that make sense? Now take this northeastern hemisphere. Take this northeastern part. This is where you are currently. Okay. Now is the location in the eastern or the western half of this? Which means you again divide this. Are you again in the east or the west? Okay. Now say for suppose your answer is eastern, then again you write a 1. Which means you are in this part. Does that make some sense? Now again deep dive. Is it again the northern or the southern half of this smaller region? Let's say your answer is north. So you again divide this. So you are saying that you are present somewhere over here. And then again you write a 1. So you get 4 ones. So you keep doing this and you keep splitting the region into smaller and smaller pieces, alternating between latitude and longitude, which means east and west and north and south. And after each split, you record your answer as 0 or 1. So after 25-30 such questions, you have narrowed down from the entire Earth into a box of about 1 kilometer square. And these zeros and ones, that is your geohash. But instead of showing it as a binary, we convert it into a base 32 shorter string. Let's come to it in a while. But this is what geohash is. I hope this makes sense. So let's take a real world example. Let's say you are in a core Mangla's location, and after these splits, you end up getting a very large geohash. This is something like a geohash. After converting this whole, again, this is not the exact geohash. This is just for reference. This is what you end up into. So you convert this into base 32. Base 32 includes characters from A to Z and then numbers from 2 to 7. Okay. So what base 32 means is that you divide these whole geohash into 5 equal chunks from right to left. And then for every chunk, you find the value in 2 to the power something, right? So this is, let's say, 2 to the power 1 plus 2 to the power 0, 0, 1, 2, 3, 4. So this is 2 to the power 3 plus 2 to the power 4. So whatever is the value corresponding to that, you will map it to either A to Z or 2 to 7. So this whole value will come from where to where? It will come from 0 to 31. Does that make sense? So for 0 to 31, you use A to Z. For 0 to 25, and then remaining you use 2 to 7. And there's extra padding as well. Okay, but again, I don't want to deep dive here. But then let's say you end up converting this geohash into something like TD1RY. Okay, now here is a restaurant, let's say which is 500 meters away from this location, which will have a geohash something like TD1Y6. Okay, and did you notice something? That they share the same prefix. they will have a similar kind of prefix. Okay, a restaurant 2 kilometers away might also have a similar prefix. Let's say this is Y2, something like this. This is Y3. Okay, so the longer the common prefix, the closer the locations are. Does this make some sense, everybody? Okay, so this is what we use for searching. So now in the restaurants table, you will store for every restaurant what is the Geohash using the same logic. Now you will create a database index on this Geohash column. You can create an index on this column, just like a common index on username or email that you create. And now whenever a user searches from Koramangala, let's say, you calculate the user's geohash. First, you calculate the user's geohash. So user's geohash could be something like TDR1Y. Now you run the SQL query. Hey, select all from restaurants where geohash is like. You drop the last character and you find this prefix in all the restaurants. And this is going to return all the restaurants where geohash will start from TD1Y, which are nothing but all the restaurants that are, say for suppose, within 1 kilometer radius around the user. You might get 200 restaurants. Now you can calculate exact distance for these 200 and not 500,000, and you are done. And why is this brilliant? Is because database indexes work perfectly. Here we are doing string prefix matching, which is lightning fast with B tree indexes. Okay, this is what databases are optimized for. And then you have an adjustable precision here. If you need a bigger search area, you can use a shorter geohash, something like TDR1 for this case. If you need a smaller area, you can use a longer hash. And this is no complex math. Your database doesn't need to understand 2D coordinates. It's just comparing strings. Geohash can go from length 1 to 12, where 1 is the whole size of the planet, and then 12 being an area of around 3.7 centimeter into 1.9 centimeter square. Right? Hence, our geohash length of interest is just from 4 to 6. This is where the radius goes from 0.5 kilometer to around 20 kilometers square. Okay. But again, there is a problem with this. The real world problem is the boundary issues. Okay. Because you can imagine this scenario that you're standing exactly at the border between two geohash regions. Okay. What happens here is that even though the distance is just 10 meters away, even though one location is just 10 meters away, it won't show up in your search because it's in a different geohash region. So the fix for this is, instead of searching only your geohash, you also search the 8 neighboring geohash regions. This ensures that you catch restaurants near boundaries as well. Okay. So it's just 9 queries instead of 1, but it still is faster than scanning 500,000 restaurants. Okay, and then there could be a scenario where you don't get enough businesses from the current hash. Then you simply can remove the last digit, increase your search area, and then use the updated geohash to try searching more nearby restaurants. Okay, and let me tell you one more thing, that Redis has support for all this geohash related stuff. Like it has support for geoadd, georadius commands. Even MongoDB supports geospatial commands, geospatial queries with geohash. Even Elasticsearch uses it for location searches. And it's very super easy to implement. It's just a library call. Okay. So it's not perfect because of the boundary issues, but for 90% of the use cases, it's good enough and much simpler than the next solution, which is QuadTrees. Okay. So now let's talk about what companies like Google Maps and Uber actually uses in production, which is QuadTrees. And this is the gold standard. What is the concept? The concept is that a quad tree is, think of it like a tree data structure where each node represents a geographic region and each node has exactly 4 children representing 4 quadrants. Okay. So think of the whole planet as one node where every node has 4 children, 4 quadrants, with every node further dividing into 4 quadrants. And you keep dividing this until you find a quadrant with less than equals to 100 restaurants. Okay, so let us see this in action. Okay, start with the whole map. So you start with the whole map. This is the whole word map as the root node. And if a region has more than n restaurants, let's say 100, you split it into 4 quadrants. And you recursively keep splitting each quadrant until every leaf node has less than equal to 100 restaurants. And by doing this, you will find that your dense areas get split more and the sparse areas stay as larger regions. Okay. For example, think of this Bangalore. Okay, so let's take a visual example of Bangalore where you have four regions. Like you have northwest, northeast, southwest, and southeast. With Yashwantpur, which is again a sparse area, let's say it stays as is. You have Whitefield on the northeast, which is again a medium dense area, which can be split once. So because overall in Whitefield you might have more than 100 restaurants. So you will split it into again four different quadrants. Then you will end up finding, okay, how many restaurants are in this area? That means how many restaurants are in the north west of Whitefield. If it is again greater than equals to 100, you will again split it into four quadrants. You keep doing this until you get less than equal to 100 restaurants in a leaf node. This is what this whole diagrammatical representation means. Okay, so let's take an example of Koramangala. In the case of Koramangala, which is a very dense area, you might again end up splitting into four different quadrants. Where in the northwest, you have, let's say, Sony signal, right, which is again dense. So you might again split it. Okay, in the northeast, you might have 100 feet road, which is again dense. You might split it again. Isn't it? Let's say in this area you have 50 restaurants. Here you have 80 restaurants. Here you have 60. Here you have 120. So you split it again. Okay, so this is, let's say, Koramangala 6th block. This is Koramangala 8th block. Again, you keep finding, okay, how many restaurants are in the 6th block? Depending upon that, you divide it. Again, you don't divide it. And you see the beauty, right? That Koramangala gets split into 3 or 4 levels deep because it is more dense. But Yashwantpur might be 1-2 levels because it is sparse. This is why this tree adapts to your data distribution. And the querying a quad tree looks simple because you start at the root node, you determine which quadrant contains your location. So check if your search circle intersects the quadrants. If yes, you can search those two, but you traverse down the tree. So at leaf nodes, you end up actually reaching those restaurants which are in your closer proximity, and then you return the results. So the time complexity overall is your tree traversal, which is order of log n, which is your height of the tree, and then you again reach the leaf node. Let's say it has k restaurants. For these k restaurants, to check in leaf node, again you do some computation that this is going to be the overall time complexity going to look like. And why will this quad tree win? Because it has adaptive density. You automatically handle dense versus sparse areas. Faster queries because now you are doing a logarithmic tree traversal. No boundary situations because you explicitly check intersecting quadrants. It is going to be again memory efficient because you only store restaurants once and your tree structure is small. Okay, so I hope this makes sense. But in the real world implementation scenarios, you will use caching for common search locations like airports, railway stations, malls, etc. You can also use sharding for global scale. You can shard by continent, shard by country, shard by state, shard by city, and so on. You will also have replication where you replicate the tree across multiple servers for high availability. And then you also have you can also use a write through cache where you update to DB immediately and then you rebuild the tree asynchronously every few minutes. Okay, to handle all the updates because businesses can keep adding or removing from it. Okay, and in the cases of businesses like Uber, your driver location keeps changing. So in that case, it's better to use a solution like QuadTree instead of a Geohash. Okay, so when to use what is like for Geohash, it's great for moderate scale where you have less than 1 million locations and you want a simpler implementation. You are okay with some boundary issues and it's perfect for small scale companies. But QuadTree is a production grade for massive scale. It's for millions of locations and you need less than 50 millisecond response times and you're willing to manage in-memory databases, in-memory data structure. You are ready to maintain that whole QuadTree in memory. And this is what all the big tech uses. Okay, and so now coming back to your original question that I was hungry and then I opened Zomato and then I saw that all the nearest restaurants within few milliseconds. So what is going to be Zomato's likely architecture here? It's going to be something like a quad tree for in-memory for ultra fast queries. And then you can also have geohashes in databases as a backup or a fallback if something fails in memory quad tree. And then you can also do a clustering by city, which is to have a separate quad tree for Bangalore versus Delhi versus Hyderabad. You can also use a CDN plus Redis caching for all the popular searches. You can use a Postgres with Postgres for persistent storage. Okay. Um, and there you have it. Okay. So from naive solution order n scans to production grade quad trees, you now understand exactly how proximity search works at scale. And what is the key lesson? The key lesson is your adapt your data structure to your data distribution. Okay. So grids assume uniformity, but Geohash is clever but has boundaries, isn't it? And quadtrees adapts to reality. So if you found this useful, smash that like button. Please drop a comment if you want me to cover more or any of these options in detail. For example, quad tree or even evenly grid distribution or the any of the other alternatives. And if you're preparing for system design interviews, these questions appear very commonly at Amazon, Google, and Uber all the time. And you're closer to clearing those rounds. So I'm Umang, and I'll see you in the next one. Happy coding, guys.